Hello, I'm Risha, and I'm a contributor on the Linkerd project, and I'm here to introduce Leo, who will be speaking to us about how his company brought a service mesh into their infrastructure and used it to serve billions of requests per day, and what they learned from that. This is a reminder also to rate each talk on sked.com after each session. Leo has a ton of industry experience with distributed systems, having worked at Microsoft, Amazon AWS, and Twitter. So let's hear what he has to say. Please welcome Leo.
Thanks for everyone here. So my name is Leo, and I actually work at, currently I'm actually working in cruise automation, a self-driving car company. This talk is actually mainly my work in my previous company, as well as actually as a role contributor of Linkerd. So here's actually my little profile. Let's actually get started. I try to actually describe a startup in Python code. This is usually how it works. In the early stage startup, somehow you actually pick a domain, right? And then that domain, you don't know the difficulty of the domain, maybe. And then you actually pick a goal, which measure in progress. And then every day, your company and your team make some progress, burn some money. And tomorrow, if you still have some money left, and you still have something to do, and do again, until some point, you either run out of money, or either you finish your progress, right? That's actually fairly simple. This is a hypothetical, fairly simple case of a startup. So this is something that you, by the way, it shouldn't be random, but this should be a function somewhere that this is something that you should actually optimize for. You want to actually maximize your iteration progress. Okay, in every single iteration, you want to actually maximize your throughput. How to do that? Usually, you actually hire a bigger team, right? And then you get every team member have better productivity, bigger team. And when you have a bigger team, what can you do? And usually, according to Communist law, and any organization that designs a system inevitably produce a design whose structure is a copy of the organizational communication structure. So that implies two things. A, you either actually design your organization first, and then you have your architectures. Your architecture mimic your organization, whatever it looks like. Or you should have an architecture first. So because this is actually not a management talk, right? It is a technical talk. We should actually focus on having the correct architecture. So this is actually where our story begins. We actually start to actually build up a new stack in 2016, very early of 2016. At that time, Linkerd just released the first version. I can't remember exactly the version number. It's 0.8 something. And at that point of the time, the company actually has 10 engineers. Okay, and then by the end of, by the mid of 2018, we have hundreds. And then 2016, there's one big fat monolith. And then 2018, we have 40 services and 300 million requests a day by that time. And by 2018, that's actually 2 billion. So if we actually measure, oh, by the way, the company stack actually purely on AWS. They actually host that on the EC2s. At that point that we have tens of boxes, and then by 2018, we have a couple hundreds of boxes at the same time. This is actually it's a fairly hyper-growth company that I actually work for. How we actually transit that from the monolith to microservice world, I actually call that service mesh-driven transitions. So first of all, let's talk about what's Linkerd, right? This talk is specific, our experience on Linkerd v1. What is Linkerd? It's a very feature-rich proxy. So it provides manageability and observability of your traffic between any 2 points. And it is actually based on a fairly sophisticated stack. Mainly the Linkerd team is actually a group of gang that actually from Twitter. So they actually built on the very mature Twitter technology at that time. It's a Netty, Finango, Scala, and Thrift. And Linkerd use a domain-specific language called DTAP for routing. Basically, it is a set of prefix matching rule. I don't want to actually get into very specific detail about DTAP here. You can actually search DTAP Finango or DTAP Linkerd. You can always actually get the information there. Named, it is actually the DNS of the service mesh. What's special about Linkerd v1 is it provides a very, very powerful architectures, allow you to actually write a code that actually intercept into its pipeline. This enables us to actually make the linkage between any 2 nodes programmable. What does it mean? That means we can actually implement filter, transformer, we can manipulate the result and manipulate the payload of the traffic between any 2 points. So what this talks about? This talk is about the architecture evolution from Monolith to a microservice driven by service mesh. In 2016, at that point, Kubernetes, DCOS are still in its very early stage. And serverless was actually on the rise. And as a startup, we can't actually bet on any kind of this technology at that point of the time. For now, I think you should feel free to actually bet on Kubernetes. That's why we are here, right? And also at the startup at that point of the time, we want to actually make our solution cluster and cloud provider relatively neutral. What this talk about is actually we try to actually present a fairly pragmatic and systematic journey about how we actually from Monolith from 1 service to like 40 services. And it's imperfect. So we are not coming here to actually present a perfect solution, but instead we try to be actually very pragmatically and realistically explain what we did and walk through the actual trade-off that we have. So this is the agenda. First, we will actually talk about edge. And then we will actually talk about the edge is actually a critical component here. We will actually deep dive into that. And then we will actually talk about how we actually build the mesh internally for the service. And then we will talk about observability. And at the end, we will actually talk about some of the learning and conclusion that we have here. So, what is the edge? An edge is a service component that exposed to public internet. And usually it acts as a gateway and it divides internal and external services. From the high level, how we actually implement the edge service is actually a combination of Nginx and Linkerd together. You may actually ask why you combine 2 proxies together, right? It's weird. I will try to explain that here. Nginx, because as a lot of startup, right, when you actually running really fast and you have a monolith, what would you do? You want to implement an API, and some engineer would just dash in and just do something and expose an interface outside, right? And then the outcome for that is usually is you have a large amount of API, they all working and used by some version of a client, but they are not actually necessarily really standardized. When you actually move from a monolith to a microservice, you really actually can't just saying, I disconnect all the old client and I need to actually shift all the old client to a new client format. It's impossible to do that. And we actually use the Nginx to actually do the URL normalization as well as actually performing policy enforcement. Linkerd is actually used as a routing here. So let's actually get through, this is a high level of what Linkerd actually look like, the pipeline actually look like. You can see the pink color, this is actually the pipeline. And then the blue thing is actually where you can actually write your plugin to inject into that in every single stage. Particularly, we will actually more focus on in the identifier stage here. So we will have a lot of example later. So, okay, let's actually get into let's get into the Nginx layer. ELB, a request actually from a mobile to ELB, and ELB actually forward the request into Nginx layer. And what Nginx actually do at that point is to perform some policy and security check. For example, dealing with CSRF header validations, and also actually doing header normalizations there, try to remove unnecessary header, inject some of the header there. And then also, this is the key part for that is, it does URL normalization. It actually translates the public URL into canonical URL that can be consumed by Linkerd. In specific, you may actually notice here, right? So in the canonical URL, we have some very special encoding here. The first part for that is /h1, it is actually the protocol. So we can actually extend that to h2 in future. And then the data center US East 1A, that's actually, obviously, that's actually where it look like is an AWS domain. And prod is a stage. So on the edge, we actually encode these things actually inside the Nginx deployment. So the Nginx will actually form the canonical URL in that form. This allows us to have multiple data centers. Let's take a look at in the Linkerd layer. When we actually have the Nginx actually pass down the canonical URL to Linkerd, what it does is the Linkerd actually throwing that canonical URL into named. Named just like a DNS, right? It will actually translate that particular path like h1 US East 1A prod /full/bar A equal to 123 become some host pod /full bar. This translation process, it is actually called resolutions. We will actually talk about the resolution process actually later, which we have actually our own development on this part that to actually play some magic to actually scale up our service. From here, you may actually notice that I have actually two, is it working, this one? There's actually two boxes here. One, it is actually the authenticator. Another one, it is actually experiment decider. They are actually the plugin in the Linkerd. So I will actually try to explain what they do and how we actually implement that in the following slide. Let's take a look at the authenticators. So when we actually, in a monolithic world, right, you have your app, and usually your app actually based on some sort of framework, right? And a lot of framework that actually come with some sort of very easy mechanism to do authentications. And authentication shouldn't be a big problem for whoever actually using a monolith approach. But in the microservice world, this is the first thing that you usually actually worry about. Because you want your engineers to actually be able to implement service in any framework that they like or in different language that they want. And you need to actually get a consistent way or easy way to actually authenticate their request. In our specific case, we were actually using Django. Django is actually based on a cookie authentication. And we then actually enable JWT, JSON Web Token, as a secondary way to actually authenticate requests. It actually imposed a challenge here. And the way that we actually solve the problem is to actually have a plugin, put that into Linkerd, and intercept every single request, and performing the validation logic actually there. And literally every single request actually coming into the edge, going through Nginx, and then actually get into the Linkerd, and then that particular request is actually run by this particular logic, the authenticator logics. What the logic actually do, it explained in this slide. On the left-hand side, it is actually the config. It actually has a proxy config and a JWT key config. Okay, and then on the right-hand side, this is actually the logic, the high-level logic actually here. The original implementation, obviously, it is actually in the JVM language that's actually in Scala. And I don't want to present the Scala here because given the fact that like it's very hard to read. So I try to reform the logic using a Python per pseudocode. So as you can see here, the logic is on the high level is fairly simple, right? First, try the JWT authentication. If it actually fails, it tries to proxy the code into your authentication service, which is a microservice actually inside your stack. In that way, we get the best of both worlds. So if something is actually, if this authentication, this particular request, it is authenticated by one of the authentication methods, it's success. And then we actually pass the identification stage to the next step. If it's not successful, we throw an exceptions. Actually, we actually return 403. So that's how authentication actually works. So we explain how authentication works. And then next step, if the request is authenticated, and then we will actually go through a secondary plugin that we have. It's called Experiment Designer. So why do we need to enable Experiment Designer? Because fundamentally, when you actually design online services, you have a lot of service actually in your stack. The first thing that you want is you want deploy anytime, right? You want multiple services being able to deploy at the same time, and then you want them to be able to do the experiment, to do progressive rollout. They don't need to actually stay in the queue, right? So this is actually enable that particular scenario. Fundamentally, we want to actually do is for service X, we need Y% of the traffic go into the X canary, respecting the request context. Why we need to, what does it mean by request context here? So just give you an example. If I am actually as a user, I send a request into your stack saying I want to actually get all the item, right? And then the item service, it is actually doing some sort of experiment for now, is rolling out a new item service version dash. What you really want is, you want, for me, for a particular user, you either actually stick with a production or canary. You don't want him to actually jump across. Every single time they refresh, they will get different endpoint. That's the terrible experience. That's what I mean by context-sensitive experiment. So we actually implement this, another plugin, actually in Linkerd. What it does is, literally using murmur hash to actually share the user ID or some sort of context that inside the request and ensure a particular user always stick with a particular service stack. So that means it's like if you have a item service actually being deployed, and then it has a canary actually enabled for any particular user at any particular point of time, they should only stick with a particular version of the your software. This is a layer to actually control based on some sort of context. So as you can see here, this is actually the high-level overview for that. So a user request comes in, it gets into your edge, and then your edge actually somehow actually synchronize with some sort of config inside S3. That particular config specific, like for particular service, X% go to this, X% go to canary, Y% go to canary V1, etc. So that plugin actually synchronize that. And what they do actually for that is, what the plugin for that do is, for every single service, it literally controlling the value of R1 and R2. So we actually allowed you to actually update the S3 file on the fly, and then the routing edge actually periodically refresh the value from the S3. Usually, it actually pick it up like in 30 seconds, and that will allow you to distribute the traffic. So Linkerd enable this particular scenario, give you a very nice programming interface to control traffic up to that granularities. Okay, this is actually what it looked like inside the edge. So on the high level, ELB, the request coming from ELB, and then the request go into Nginx, and Nginx normalize the URL and forward that to Linkerd. And Linkerd actually has couples of plugins. The first one acting as a filter, and acting as a second one acting as a transformer, and then after the request is done, they deliver to some sort of endpoint. The endpoint can be service, another set of service, or it can be actually a API gateway, which is mounting the service list, a service list stack. So here are pros and cons. The pros for that is we now actually have a horizontal scale ready stack. So you just add more boxes when the traffic comes. It gives you a flexibility. It's very flexible because Nginx is super powerful. Linkerd is super programmable, and then you get the best of both worlds, and you have the full observability from Linkerd as well. What's the con? What's the downside for that? Probably you may actually ask. We are doing double passing, which is a request going into Nginx and then going into Linkerd. So what's the trade-off for that? We actually waste 50% of the CPU. So, well, this is actually a trade-off that we have for this kind of flexibility. It's because the number of the edge boxes that we have is actually range from 3 to 30 through the day, because our traffic is actually very time sensitive. So we actually use like 50%, 100% more of the CPU there. But given this flexibility and given the capacity that we have, we actually decide that this is actually a good trade-off for us. So let's get into, we talk about the edge. Let's actually get into the mesh. Okay, so let's talk about the microservices that we have. We want to, at the beginning of the design, in the design sessions, we talk about what we want as a company. Okay, we want to be able to enable the engineer to use the best tool for the best purpose. What does it mean? It usually means it's like it need to actually support a lot of languages. Okay, not all the language. We end up actually deciding we support Java, Python, and Go. We want to actually support different kind of framework that each of language actually really good at. We want to support different kind of messaging protocol, specific REST, HTTP 1, and Thrift. And then now the challenge actually for that is, in this very hybrid or heterogeneous environment, the challenge actually for us as a platform engineering is, it's a super challenge to really actually manage all these different kinds of traffic, because if any of you have been actually playing with Java or playing with Python, then you actually know how difficult to really getting the connection pool actually correctly set up, right, in the specific framework. That's usually is a mission impossible. And if you multiply by like the number of the framework, the number of the language itself, that's actually pretty much is not a very enjoyable work. So Linkerd is actually here to actually rescue. Linkerd is actually, as we actually mentioned, our service stack is actually on EC2 boxes at that point. So we actually deploy Linkerd as a sidecar. As you can actually see that from this graph here, from an application standpoint, the application has no external touch point. That means all the traffic actually getting into the application is from localhost, which is from the Linkerd sidecar, because every single traffic actually getting into the box always gets through the Linkerd, and Linkerd actually forwards into the applications. And when the application need to actually reach out, and then we have the firewall, we don't allow the application to actually reach out directly. It has to actually go through the Linkerd itself. Why? Because this way, we have a fairly consistent connection pool management policy. We have a really good circuit breaking, and we have full observability. That's actually what Linkerd actually provide. And also, when we have backpressure, which means backpressure really means it's like if some of the service actually like act really weird, sometimes mainly because of like your database slowdown or things like that, your application use up all your thread pool, and then everyone depends on that service, actually feel the pressure actually back from that particular, the service actually in difficulties. And at that point of the time, the circuit breaking or the retry policy of the Linkerd actually kick in, and we actually, as a platform engineering, that can actually control this set of policy and to actually yield a desirable behavior. So when incident actually comes in, and we know how much bomb a particular stack that can actually absorb. It's very critical for the stability of the service. So as you can see here, Linkerd is actually running as a sidecar inside the box. And we also have an announcer. You see this is another box. This is another plugin that we actually write. We'll actually go into detail later. Oh, by the way, you see that on the egress point here, we also have an experiment designer. What does it mean? It means when you actually enable a progressive rollout, say, I am trying to roll out a new item service, and all your internal service that need to talk to the item service, also respecting your rollout config. So that means if you say for 5% of the traffic go to the new item service, and then because your item service has two main sources of the traffic coming from, right? First part is actually from external. The second part is from internal. And by having a egress, in the egress, we actually install our plugin in that way. That will actually enable us to actually doing the rollout even for internal traffics. So we just finished the overview about of what the service mesh look like. And in specific, I want to actually talk to one of the very fun topic, how service and service talk to each other. I named this part actually called discovery. We actually have two stages. We evolve our stack in two phases. One is discovery V1, and the other part is discovery V2. Let me get into the detail here. So discovery V1. It's fairly simple. This one, the diagram actually looks much complicated than the actual solutions. It is actually this part, we actually use console. So we statically actually register the service in the console by the ELB name. So on the high level, what discovery actually does is to mapping from a service to either a host or either a DNS or either a bunch of IP, right? So this is what it does. We actually statically actually register the service into console. So we have a name mapping to a particular ELB. And with the help of named, every single request actually coming in here, and named will actually tell the Linkerd the IP address of a ELB, okay? And then the request is going from there. As you can actually see that is, now for every single service talk to the other service, always going through a particular ELB. It's all good, right? It's fairly simple. But there's a problem. First, DNS is not the best way to actually do load balancing. Why? Because the client always actually cache the DNS. And whenever you have caching, and then you need to actually talk about eviction, talk about all the other stuff, that is fairly complicated. And also, more importantly, a lot of the very fancy or matured feature is actually host-based. What does it mean? Retry budget, right? Whenever a host actually start to fail, and then we retry, it's based on the host. And circuit breaking is based on the host. So if you want to do the retry budget or do the circuit breaking actually on a ELB, in that sense, anything goes wrong, and then you shut down the particular ELB, you lost the content of all the hosts behind that particular ELB, which is not a good idea. And that makes ELB literally become a single point of failure. How are we going to fix it? Discovery v2. Discovery v2 is SRV based. We use SRV based routing. It's actually per node. It's actually peer-to-peer. What does it mean? We go around the ELB. We don't use the ELB anymore. We actually enable hosts to talk to the other hosts directly on the fly. And fortunately, Linkerd can actually do that fairly easily because Finango actually support different kind of load balancing algorithm. It's very mature. Let's get through what SRV is. SRV, it is a kind of DNS record. You can consider that as a CNAME for a group of hosts. I think every DNS provider nowadays actually support that. Particularly, we actually use in Route 53. In each of the SRV record, I remember that will allow us to support up to 200 hosts. So basically, if you have a service, you give a DNS name of a particular service, it allows you to add 200 nodes under that. And then the SRV record is actually contained with this special format. It actually has priority, weight, and port, and the actual host itself. So this is how it works. Because every single EC2 box, we call that a node. Node automatically actually announces to a FleetDB. FleetDB is a database that we implement that using a Dynamo to actually implement the FleetDB with some sort of decay. And FleetSync service actually listen to the FleetDB using Dynamo stream, and then register the DNS, the new coming DNS into Route 53, and deregister things that has been already actually expired. And we actually implement a SRV record resolver in the named. So named now understand SRV record. And whenever a request coming into a Linkerd dedicate the resolution to named give it Linkerd back a list of the hosts. And Linkerd can actually do the load balancing locally. And the FleetSync service, the thing that in the yellow box, what it does, it is actually a free-form service that actually running in a Lambda. And we periodically actually wake up that particular Lambda. It actually use that to actually monitor the FleetDB and listen to EC2 event when a EC2 box actually die, and then it try to remove that entry, and it also try to periodically rip off the outdated informations. In this design, obviously, one of the key things that we actually trade off, it is actually consistency. So basically, whenever at any point of the time, when you actually get back a list of the IP that you want to balance to, it's possible that some of the IP may be already outdated for that particular service, which is fine in our case because Linkerd actually is a load balancer itself. It knows how to, whenever they actually try to talk to a node that actually dead, they will actually try to rotate to another one. And it actually maintain a balance, the load balancer set actually in memory. And availability is actually strong, and fault tolerance is strong thanks to we actually use the cloud-based solution like Route 53, DynamoDB. So we don't need to maintain those infrastructures. And particularly in this way, we no longer need to actually maintain the console. So because console is a very good product, but just until that it failed the master and then get into the master election, then that's another nightmare. We no longer have those kind of problem. Okay, this is a result. The graph, it is actually the new connection count. So before, after. So before we deploy the service, and then you can see that we have a lot of new connections. After we actually deploy the service, we can actually see that the new connection actually drops significantly, because Linkerd to Linkerd connections is actually much more well-behaved than Linkerd to ELB and ELB to Linkerd. So ELB actually get removed it, and then we have a much more stable connection pool in some sense. This is another graph. This is a latency graph. The yellow, it is a P99. Green is a P50. That's before and after. So when we actually deploy that, and after we actually deploy that, our P99 become P50, literally. And we actually confirm that in the ELB, by observing this data, we actually confirm that like on the ELB usually introduce like 1 to 2 ms of the latency, and then quite a lot actually for the P99. As you can actually see that in the P99, there's a much bigger bump in there, and then after we deploy that, those bumps no longer exist. So discovery V1 versus discovery V2. So observability. How we actually getting the metrics is actually very important here. We actually use Prometheus and Grafana to actually building our dashboards. Remember, we have the FlipDB, right? So that makes the whole story actually much simpler at that point. Okay. So we actually use the Prometheus to actually pull the FlipDB, and then the Prometheus actually periodically updating it, and then we have the full observability. We actually collect 500,000 metrics point and 10-second interval and 40+ services. So let me show you some graph before the end of the talk. So this is actually a rollout graph. The green, it is actually the old service. The yellow is the new service. And then on the right-hand side, that's actually up to per box level. And this is actually the breakdown for particular service from the ingress. So yeah, that's it. So in conclusions, we now actually have a full service mesh that actually fully observable and fully controllable, and then direct connect without ELB and node-to-node level. And thanks to JVM 9, and then we also observe a huge drop of the P99 due to like much smoother GC latencies. Yes, and thank you.